Imagine a Michelin star kitchen, right? But the chefs, they have absolutely no idea who they are cooking for.
Right. No table numbers, no pacing.
Exactly. Just these anonymous tickets getting shoved under a door, that blind chaos. That is actually exactly how your company's database is operating right now.
Really is.
Every query gets treated like this isolated, contextless emergency. So, welcome to this deep dive. Today, we are exploring a fundamental, completely hidden flaw in how we build and interact with data systems.
And we are pulling from a really fascinating piece written in January 2026 by Yuri Rashkovsky.
Yeah, the founder of Inferral.
Right. And the piece is titled, Databases Don't Know Why You're Asking.
It's such a great title.
It really sets it up.
Mm-hmm.
The mission for our analysis today is to dissect this blind spot, what the source material calls the hidden assumption, and unpack Inferral's shift away from databases that simply answer isolated questions.
Towards systems that actually participate, right?
Yeah, exactly. Systems that participate in your business processes. Because, we have spent decades aggressively optimizing databases.
Yeah.
Faster indexes, smarter caching layers.
All to answer queries in like milliseconds.
Right. But we have completely ignored the fact that the database has no idea why it's answering the question in the first place.
Okay, let's unpack this. Because that lack of context is what Rashkovsky argues is basically breaking modern architecture.
It is.
The database, it doesn't know if a query is, pulling a number for a high-frequency trading algorithm that needs to execute in a microsecond, or if it's just generating some internal sales report.
Right, a report that literally no one will look at until next Tuesday.
Exactly. And because it is completely blind to the business outcome, it just defaults to panic mode. It assumes every single request requires maximum urgency and, perfect mathematically rigorous consistency.
What's fascinating here is how this plays out in the real world. Let's ground this in a practical scenario from the text, the e-commerce checkout flow.
Oh, yeah, this is a great example.
So when you buy something online and hit place order, you, the user, experience one continuous action. And the business logic also sees a unified process.
Right, it's a sequence. Reserve the inventory, charge the credit card, finalize the order, and then eventually send a confirmation email.
Yes. The business knows there is a strict hierarchy of importance there. The payment absolutely must clear before the order is finalized.
But that confirmation email, if the email server is lagging, the business knows it shouldn't crash the entire checkout process over that. It can wait.
Exactly. But the database, however, it doesn't see a checkout flow. It just sees what Rashkovsky calls fresh strangers.
Fresh strangers, I love that term.
Right. The application sends an isolated command to update the inventory table. Then, 50 milliseconds later, a completely separate command arrives to update the payment ledger.
Then another one to log the email trigger.
And the database treats the inventory lock and the email log with the exact same level of blind, isolated urgency.
And the danger of that isolation becomes super obvious the second something breaks mid-flow.
Oh, completely.
Let's say the database successfully locks the inventory and logs the payment, but then a network blip occurs before the final order creation query arrives.
Right. Happens all the time.
Because the database was just processing a disconnected sequence of strangers, it has no overarching awareness of the transaction as a business concept.
It doesn't know how to automatically repair the state.
Leaving the engineering team to clean up the mess, the customer's credit card was charged, but no order exists.
Which is a nightmare.
To fix this, you are forced to write what we call compensatory transactions. Basically, you have to build these custom manual cleanup scripts to comb through the database, find orphan payments, and issue refunds.
All because the foundational data layer didn't understand the process it was participating in. Which brings us to the core argument of this source material.
Right.
Because the database is blind and assumes the worst, it forces engineering teams to pay massive, hidden infrastructure costs. Rashkovsky frames these as three specific taxes.
Let's go through them.
So the first is the urgency tax. Querying a standard database is inherently synchronous and time-sensitive.
Meaning when your application code asks for data, the executing thread literally halts and waits for the response.
Exactly. And a block thread consumes memory. If the database slows down, those waiting threads just pile up, exhausting your connection pools.
And eventually, the entire application server crashes.
Boom. Done.
So to avoid that, Engineers have to build these incredibly defensive parameters around the database. We hard code aggressive timeouts.
Right.
We implement circuit breakers, which literally sever the connection to the database if it gets too slow. We intentionally fail user requests just to prevent the system from going down.
You had military-grade lockdown.
Yeah, for every single query. Regardless of whether it's a critical payment or, a background analytics job, simply because the database can't tell the difference.
Now, the second penalty is the consistency tax. A database has to maintain perfect consistency constantly, just in case a query arrives that demands it.
And the most common manifestation of this is indexing. Every database engineer knows the rule add indexes, but not too many. Let's evolve the standard analogy here. We usually compare an index to a textbook index, but in a modern digital system, it's not like a book.
No, it's way more dynamic.
It's more like trying to run a live GPS tracking map of every delivery truck in a massive fleet. You are constantly burning computational fuel to update the exact coordinates of every truck the millisecond they move an inch.
And you're doing that even if the dispatcher went home for the night and no one is actually looking at the screen.
That is the consistency tax right there.
Right. Every time you insert a new row of data, the database stops and immediately recalculates the index. It pays that compute cost upfront on every single write.
Just anticipating that a read query might arrive at any microsecond. Go, wait, I need to challenge this idea.
Sure.
If the solution is deferring that work, say, the business knows the dispatcher isn't looking at the map until 8 a.m., so we just don't update the index until then. Aren't we just building up a massive mountain of technical debt?
How do you mean?
Well, if a sudden unexpected spike in traffic happens at 7 a.m. and someone runs a query, wouldn't the database completely lock up trying to calculate 8 hours of missing index updates all at once?
See, that is exactly what would happen in a traditional architecture, and it's why database engineers are so terrified of deferred indexing.
Right.
If the database is blind, you absolutely must pay the tax up front. But Farrell's argument relies on the system having structural awareness.
Okay.
If the data system actually manages the entire business process, if it acts as the orchestrator, it knows exactly when that dispatcher query is scheduled to run.
Oh, I see.
Yeah, it dynamically allocates resources to process the batch of index updates quietly in the background at, say, 7:55 a.m. It avoids the traffic spike crash because it isn't guessing. It controls the schedule.
Oh, wow. That distinction makes a lot of sense. It shifts from reactive guessing to proactive scheduling.
Exactly.
Which ties perfectly into the third tax being preemptively optimized. Because traditional databases are always guessing, we just throw expensive hardware at them.
We keep massive memory buffers hot.
Yeah, we cache query execution plans based on statistical probabilities of what users might ask for. We burn RAM and CPU cycles anticipating demand that might never even materialize.
If we connect this to the bigger picture, every single one of these taxes, the circuit breakers, the immediate synchronous indexing, the over-provisioned RAM, they are entirely logical engineering responses.
Right. Engineers aren't stupid.
Exactly. But they are logical responses to a fundamentally broken baseline.
Here's where it gets really interesting. So we pay all these taxes, but surely engineers have tried to fix this. How have we survived this long?
Band-aids. Lots of them.
Right. If you're listening to this and you've spent the last 3 weeks wrestling with a Kafka queue just to get a checkout email to send properly without blocking the main thread, you know exactly what this complexity feels like.
Oh, the pain is real.
We've built an entire industry of Band-Aids to route around the database, treating everything as an emergency. We use read replicas.
Yeah, continuously cloning the primary database to a secondary server, just tolerating the replication lag so the analytics team can run heavy reports without tanking the transactional system.
And we use message brokers like Kafka. If a task can wait, we just completely bypass the database and push the data into an async queue.
And then manually write the code to ensure those messages are delivered, processed, and retried if they fail.
It's so much extra work, and the most extreme example is CQRS command query responsibility segregation.
Oh, yeah.
In plain terms, we literally rip the database architecture in half. We build one system optimized entirely for writing data, and a completely separate mirrored system optimized entirely for reading data.
And then we pray they stay in sync.
We really do. The overhead is staggering. Instead of managing one piece of infrastructure, you are maintaining a primary cluster, 3 read replicas, a distributed Kafka queue, and a totally separate read model architecture.
Right. You have multiplied your surface area for bugs edge cases, and network failures by a factor of 10.
All to babysit a primary database that still fundamentally does not understand your business process.
And this is the pivot point of the source material, recognizing that adding more infrastructure doesn't solve the core amnesia.
So what's the cure?
Inferal's proposed cure isn't about, slapping a generative AI model on top of the database to make it smart.
Right, not that kind of AI.
No, it's about simple structural awareness. It's about merging the business logic with the data layer so the system actually knows the dependency graph of your processes.
Okay, let's define that dependency graph mechanically. Instead of an application sending a command that says update inventory, the application registers a process.
Right.
It says this inventory update is step 2 of a checkout flow.
Right.
Step 3 is the payment API. Step 4 is the email.
Yes, and by doing that, you unlock what Rethinking calls being fast where it matters.
Fast where it matters.
The system can look at the graph and recognize that the inventory and payment steps are blocking a human staring at a loading screen. So it throws maximum I/O priority at those tasks.
But it sees the email step and deprioritizes it, handling it asynchronously without you having to manually wire up a Kafka queue.
Exactly. It also gives you consistency on demand. Going back to our index discussion, you no longer need perfect consistency across the entire database at all times.
Because it knows when it's needed.
Right. The system can enforce strong consistency for the financial ledger during the checkout flow, but allow eventual consistency for the user's order history page.
Saving massive computational overhead. And how this reimagines latency is the part of the text that really challenges standard engineering practices.
It really flips it on its head.
Typically, latency, the physical time it takes to retrieve data over a network or from a disk, is the ultimate enemy of the database engineer. We fight latency by keeping everything in a hyper-fast, incredibly expensive memory.
Right.
But Rethinking argues that latency is really just a problem of unpredictable timing.
Which is a profound shift in thinking. If a query is unpredictable, the data must be in RAM, or the application just hangs while the disk spins up to find it.
Yeah.
But if the system is structurally aware of the business process, it knows the future. It knows what data will be needed in 3 seconds.
He uses the example of storing transactional data in Amazon S3. Which, for context, S3 is a highly durable, incredibly cheap cloud storage service, but it has high latency.
Yeah, running a traditional synchronous transactional database directly off S3 is universally considered a terrible idea.
You would be laughed out of the room. Fetching data just takes too long.
But look at the mechanics of prefetching in an aware system. Let's say a user starts a complex onboarding workflow.
Okay.
The system's dependency graph shows that step 4, which happens roughly 10 seconds from now, requires cross-referencing a massive data set of historical zip codes.
Now, a traditional database wouldn't know about that zip code requirement until step 4 actually occurs, resulting in a sudden, latency-heavy query.
Precisely. But Inferal Scheduler sees step 4 coming the moment step 1 begins.
Oh, well.
While the user is filling out their name and password, the scheduler silently reaches out to the high-latency S3 bucket, pulls the zip code data, and moves it into local memory.
So by the time the user hits step 4, the data is already there.
Exactly.
Yeah.
You get the cost benefits of cheap, cold storage, but the user experiences zero latency because the system stopped guessing and started anticipating.
I want to push on the mechanics of this, though.
Yep.
This raises an important question. How do we actually execute this?
That is the big question.
Every tool, framework, and mental model we have for backend engineering is built around writing client-initiated queries. An application asks a question, the database answers. How do you build a system that functions without traditional queries?
You have to change how you declare your logic. In Inferal's model, you don't write procedural scripts. Do this, then do that.
Right.
You write declarations of state. You define a rule. Like, an order is considered placed when a web request exists, and the payment gateway confirms capture, and the inventory service confirms stock.
So you aren't writing the imperative steps to execute the checkout. You are literally just handing the system the conditions for success.
Yes, you are handing the system standing orders. A standing order isn't a transient query. It is a permanent declaration of intent residing within the data system itself.
The business logic and the data are no longer separated by a network boundary. They live together.
Exactly.
And the engine that executes these standing orders is the scheduler. This isn't just a simple cron job task runner. Inferal is describing a scheduler that acts more like the orchestrator of an operating system.
Right. because it holds all the standing orders. It holds the entire dependency graph of your business. It sees every moving piece.
And the scheduler physically manages the compute threads and the input-output operations differently.
Very differently. In a traditional setup, the operating system's CPU scheduler and the database's query planner are fighting each other.
Yeah, largely blind to what the other is prioritizing.
All right. Infernal Scheduler unifies them. It orchestrates the network requests, the disk reads, and the CPU allocation based directly on the business graph.
So if a third-party payment API is running slow, a traditional application thread would just sit there blocked, eating up memory.
But Infernal Scheduler sees the delay, pauses the execution of that specific graph branch, frees up the compute resources for other tasks, and seamlessly resumes the checkout flow only when the payment API finally responds.
The data flows according to the declared business rules, not a brittle sequence of isolated network requests.
Exactly. It completely removes the need for the application developer to manually write retry logic or manage distributed locks or build those compensatory transactions we talked about.
The scheduler just handles the state transitions natively. So what does this all mean?
It leads us to the ultimate synthesis of Reshkovsky's vision. We're moving away from databases as passive storage engines and moving toward data-native operating systems.
Yeah.
We are entering an era of incredibly complex agent-augmented software. You will have AI agents making autonomous decisions, triggering dozens of cascading workflows simultaneously.
And you simply cannot run those future systems on amnesiac databases?
No, the infrastructure would collapse under the weight of the band-aids.
You can't rely on humans manually configuring Kafka topics and provisioning read replicas fast enough to keep up with agentic workflows. The infrastructure itself has to become process-aware. It has to participate.
It's a structural evolution. A system that doesn't know why you're asking is forced to guess. And, well, guessing just doesn't scale.
So, bringing this all back to you, the listener, the next time you are staring at a Datadog dashboard, dealing with a stressful system bottleneck, or, agonizing over whether to add yet another index to a massive table and risk slowing down your writes?
Step back.
Yeah, step back and ask yourself, does my data system actually know why it's working so hard right now? Or is it just panicking in the dark?
Because if your system is panicking in the dark, any hardware you throw at it isn't really solving the bottleneck. You are just paying another tax on its amnesia.
And that leads to a final provocative thought to mull over. If data systems do evolve this way, if Inferal's vision of a data-native OS takes hold and the infrastructure fully understands our business logic, manages its own I/O, and orchestrates its own resources through standing orders, what happens to the traditional role of the back-end engineer?
It challenges the very definition of the job.
For decades, back-end engineering has essentially been, well, high-end plumbing. We manually wire disconnected pieces together. We write the complex transactional queries. We set up the message brokers. We configure the cache and validation.
Right.
If the database becomes an aware operating system that handles the how and the when natively, does the back-end engineer's job shift entirely away from plumbing infrastructure? Do we stop writing queries and purely become designers of business rules?
The choreographer of outcomes rather than a mechanic of isolated requests.
The role elevates from managing transient state to strictly defining business intent. The machine handles the execution graph.
It means finally letting the kitchen see the dining room.
I love that. Thank you so much for joining us on this deep dive. It's been an absolute blast dissecting the hidden assumptions in our infrastructure with you. Until next time, keep questioning the baseline, and we will catch you on the next one.